Hey guys, welcome back to Physics Unit 5. I'm going to mark your tests. I've been lazy. I'll mark them this weekend and hand them back to you, alright? Momentum. Our next unit is our 5th unit. We're going to just do 6 units in the course. Momentum, and then special relativity. And so we'll do one every 2 weeks or so. So this one will take 2 weeks, and then special relativity will take 2 weeks, and we'll be done. And you'll be ready for university with that stuff, I think. So what is momentum in physics? A momentum in physics it's just kind of a contrived value that we look at. Now, what we did for energy, let's look at energy really quickly. Conservation of energy, and that was unit 4, and we said, okay, well, if we have a system going on of a bunch of masses or whatever, then the initial kinetic energy plus the initial potential energy will always equal the kinetic final energy plus the final potential energy plus some sort of energy loss. And most of the time we didn't deal with energy loss because, it's a physics textbook. We're not looking at necessarily friction or dissipative forces too often until we get a little more advanced. And one thing we did in particular was we looked at this potential energy due to gravity, right? And we said that that was equal to mg times the change in height. Okay, and when I talked about that as well, I put it in a variable where I said it's mgx, right? And where x is this direction or whatever. And I was talking a little bit about the derivatives, and if you've taken this in calculus, we said that the derivative of the potential energy with respect to the distance, the x direction, actually equaled mg, right? And that was the force on the actual object. So the derivative of potential energy with respect to the direction x, which is just our up or down direction, was actually equal to mg, which is just the force on our mass there. So why is that important, and do we need to know it? Not for this class, but it's important if you know the force on an object, which is oftentimes the only thing we really know, right? If you know the force on the object, then you can figure out the potential energy that object is able to store. So with the spring, we knew the force was equal to negative F k times x, and x was like how much it stretched from equilibrium. So if I need to know, where'd my pen go here? If I need to know the potential energy on my spring, all I need to do is find some sort of function that would give me as its derivative this value. And we figured out that it was 1/2 k x squared. No minus sign, actually. And the reason why we didn't have that minus sign is because we can kind of arbitrarily choose which where our potential energy is 0 at, and because we don't really want a negative potential energy, we make sure our potential energy is always positive, so we don't have a negative sign there. But there you go, that's kind of like a backwards derivative. It's actually what you call an integral. You'll learn that in first year university. Okay. Okay, so why would you use derivatives? Well, derivatives are important in physics when things are changing constantly, and we don't really ever get to use them because you don't learn them until grade 12, but they're really important in physics because in physics you're learning about stuff that's constantly changing. Okay, so that was our potential energy. Do we have an analog for that with kinetic energy? Here's my kinetic energy formula. It was equal to 1/2 mv squared. Momentum is defined as P equals mv. This is called the momentum of an object. Momentum of an object, and with mass m, and velocity v. Velocity is a vector, so momentum must be a vector. Okay. Its units are kilogram meters per second. There's no special unit for momentum. Well, it just seems kind of arbitrary that we would say, okay, well, we're going to take some thing's mass times it by its velocity and make this whole new unit up. I mean, what purpose does that have? What we're going to see later is that the initial momentum of any system is always equal to the final momentum of any system. There is no such thing as momentum loss, no momentum loss. Conservation of momentum. You don't get momentum loss like you would in the energy equation. So it's a really nice way to look at collisions. We use it to look at collisions between things. Collisions. Because we don't lose any momentum, so our initial equals our final. Also, it's a vector, which is nice because the momentum in the x direction will have to equal the momentum in the initial x direction momentum will have to equal the initial final momentum. So px will have to equal pix will have to equal pif, and piy will have to equal pfx, and piy will have to equal pfy. So because x and y are completely independent of each other. So when we look at collisions, this is a super useful tool for us to see what happens, and if we know the directions that two things are coming at when they hit each other and their masses, then we'll know where they're going to end up afterwards. And we can't do that with the energy conservation equation because when things smash into each other, they lose energy. Okay, so the only way we could do it with the energy equation is if we knew that they weren't losing any energy when they hit, but that's a super unrealistic thing to do. So excuse me. That's why we need this momentum variable. So the first section of the textbook is just like, here's the mass, here's the velocity, what's the momentum kind of thing. Where this value also comes from, which I think is kind of interesting, which you don't need to know, is that if you take the derivative of your kinetic energy with respect to the variable v, the velocity, you end up with the momentum, right? So there's no vector there, but the vector is the momentum is in the direction of v. So that's kind of neat. You can do stuff with that later on in special relativity. We're going to figure out the equation E equals mc. Whoa, let me erase that. Where's my eraser? I don't know if you guys have ever heard of this equation before, but it is E equals mc squared. The energy of an object moving really, really fast is equal to its mass times the speed of light squared. Which ends up just being a huge energy, right? Speed of light is like 3 times 30 million. 3 times 10 to the 8, 300 million meters per second. If you square that number, and any little tiny mass you throw in there, you get huge amounts of energy out of it. Does that mean that, this little pen I'm holding in my hand is going to explode and kill me? No. But it means that if I wanted to take every single atom out of this pen and pull them apart and place them in jars far apart from each other, I wouldn't be able to do it because there's not enough energy in the solar system to do that, probably. So we'll learn about that. It's going to be kind of neat. But today we'll just look at momentum to start, really basic. One other formula for momentum that we use, if we take this equation, which is force equals mass times acceleration, right? And we say that force is equal to the mass times the change in velocity over the change in time. That's the definition of acceleration. And then we rewrite that to say that this is mf minus, or vf minus vi over change in time, like that. And this equals mvf like that minus mvi like that, all divided by delta time. These are just momentum definitions. This is the final momentum, mvf, and this is the initial momentum, mvi. This is all divided by delta time. And so if I rewrite this as the change in momentum, that's what pf minus pi means, then you see I get a formula for my force in terms of momentum. It's just a lot of rearranging of variables, but my force is equal to my change in momentum over my change in time. And what do you know? That's another kind of derivative. If I wanted to think about that as a derivative, I would say that the force is equal to the change in momentum over the change in time. These triangles, essentially, when the space between them gets really, really small, you just put a little letter d, and then it's kind of like a derivative, right? If I'm looking at a function's change from here to here, right? And my function is p as a function of time, so this is my p variable, this is my time variable, then this little rise, or this is it's going down, but this would be my delta p, and this little run would be delta t. If I shrink this change so small that as I zoom in, these changes become like infinitesimally small, then I get rid of my little triangle and I put a little d to say I'm in calculus world now, and I'm going to use my little calculus tricks to figure it out, as opposed to just like using old-fashioned rise and run. Notice the smaller I get down, the smaller my triangle gets, the more accurate I get, right? The more exacting my slope becomes, which is what a derivative is finding. It's finding a slope of a function. So that's kind of neat. The force of an object is equal to the change in its momentum over the change in time, or the derivative of momentum with respect to time, right? So one other way to rearrange this would to say that the change in momentum of an object is equal to its force on the object times the change in time. Sometimes this is given the name impulse, and it's a way to explore some physics where a force happens, a really crazy force happens over a really small time. Like, let's say a tennis ball or baseball hitting a baseball bat. I mean, we can't really analyze what's going on in that because the force is really, really insane. You have a really fast ball switching directions almost instantly in this brief amount of time. But we can use this formula to look at some of the basic things as to what's happening. So the questions in section 5.1, for now, I probably won't even do any practice ones. Just keep this video short. But the questions in 5.1 are like fill in the blanks for the formula. So this would have been like a 10-minute lesson, 15-minute lesson in class as well. Okay, so try 5.1 number, I don't know, try them all. They're all really easy. They're going to take you like 5 minutes to do those questions, number 1 through 11. If you have any questions you don't get, or they seem worded weird, then skip them. Okay, because I don't word questions weird on my tests or quizzes typically. If there's any communication questions, don't worry about those either. We can't really do those if I'm not in the classroom with you. So we're just going to learn the basics. I think this calculus stuff is kind of interesting, especially second semester. Once you learn a little bit of calculus, you can see how it works its way into physics. It makes physics a lot more interesting, the math anyways. So try those questions. Let me know how they go. I'll give you your marks back for your test on Unit 4 by Monday. And yeah, we'll keep working on momentum. We'll start getting into some collisions a little bit. And do some math with those as well. We'll talk soon. Bye, everybody.